Good morning, all of you. In this session, I am going to explain about design of muff or sleeve coupling. In this session, I will explain a simple example on sleeve coupling. Now, these are the important conversions. 1 Pascal equal to 1 Newton per meter square. Okay, 1 megapascal equal to 10 power 6 Newton per meter square. Okay, 1 mega equal 10 power 6, 1 pascal equal Newton per meter square. Okay. Same 1 megapascal also equal to 1 Newton per mm square. Okay, 1 megapascal equal to 1 Newton per mm square, or 1 megapascal equal to 10 power 6 Newton per meter square. Okay. 1 gigapascal equal to 1 giga equal to 10 power 9, 1 pascal equal to Newton per meter square. In similar way, 1 gigapascal equal to 10 power 3 Newton per mm square. Okay, these are very important for problems. Okay, and this is a solid shaft. Capital D is the outer diameter of a solid shaft. Here, this one is a hollow shaft. Capital D is the outer diameter of a hollow shaft, and small d is the inner diameter of a hollow shaft. Here, small k is the diameter ratio, internal diameter to the outer diameter. This is the cross-section area of a solid shaft. This is the cross-sectional area of a hollow shaft. Capital R is the outer radius of the shaft, hollow shaft and solid shaft. Whereas already we know that power transmitted by the shaft, power P equal to torque transmitted by shaft into angular velocity of a shaft. Okay, power P equal to torque into angular velocity. Okay, so power P equal to T into omega. Here omega equal to 2 pi n by 60. Okay, power P equal to torque into 2 pi n by 60. Okay, omega equal to 2 pi n by 60. From this equation, you can get the value of torque T equal to 60 into P by 2 pi n. Okay, this is the formula for mean torque. Okay, mean torque. If you want to design a solid shaft on the basis of strength, then you have to use this formula. From torsional equation, tau by R equal to T by J equal to C into theta by L. From torsional equation, you can get the value of torque for solid shaft. Torque T equal to pi d cube by 16 into tau. Okay, pi d cube by 16 into tau. Tau is the shear stress induced in the shaft material. D is the outer diameter of the shaft. Okay, so here from this equation, torque T equals 60 into P by 2 pi n, we can get the value of mean torque. After getting the mean torque, we have to substitute that value, torque value, in this equation. After substituting the value of T, you can get the value of outer diameter T. Okay, so this formula is used for design of solid shaft on the basis of strength. In similar way, for design of hollow shafts on the basis of strength, we have to use this formula. Torque for hollow shaft, torque T equal to pi d naught cube, pi d cube by 16 into tau into 1 minus k power 4. Here k is equal to inner diameter by outer diameter. Okay. For getting the outer diameter of the hollow shaft, we have to substitute the value of torque T. Okay. In similar way, if you want to design a shaft on the basis of stiffness or rigidity, then you have to use this formula. From torsional equation, T by J equal to C into theta by L. Okay, you can get the value of shaft diameter on the basis of rigidity or stiffness. Okay, Here capital C is the shear modulus or modulus of rigidity. Theta is the angle of twist in radians. L is the length of the shaft. And here J is the polar moment of inertia. Okay. So for here J equal to polar moment of inertia. For solid shaft, J equal to pi d power 4 by 32. Okay. J equal to inertia, moment of inertia about x axis and plus moment of inertia about y axis. Okay. J for solid shaft equal to pi d power 4 by 32. In similar way, polar moment of inertia for hollow shaft, J equal to pi d power 4 by 32 into 1 minus k power 4. Okay, k equal to inner diameter by outer diameter. Okay. So these formulas are very important for design of solid and hollow shafts. Okay. Now these are the important formulas for design of sunk case. After getting the torque, after getting the mean torque, you have to use that mean torque for design of case. Okay. Here, this is the formula for torque transmitted by the key on the shaft material. Torque T equal to pi d cube by 16 to tau for solid shaft. Okay. This formula is also used for design of keys. Torque acting on the key. Torque T equal to tangential force acting on the key into d by 2 is the radius of the shaft. Okay. Here L is the length of the shaft, W is the width of the key, T is the thickness of the key. The length, width and thickness are the dimensions for sunk case. The length of the key always depends upon the length of the length of the coupling or length of the sleeve or length of the hub. Okay. W equal to D by 4, T thickness T equal to D by 6. Now, if you want to check these dimensions, then you have to use this formula for design of key on the basis of shearing strength. Torque T equal to length of the key into width of the key into shear stress induced in the key material into radius of the shaft. Okay. From this equation, you can check the value of L. Now, this formula is used for design of key on the basis of crushing strength. T equal to L into T by 2 into sigma C into D by 2. Length of the key into thickness of the key by 2 into sigma C is the crushing stress. Crushing stress or compressive stress induced in the key material into radius of the shaft. Okay. These all are important for design of sunk keys. Okay. Now I am going to explain about the design procedure of a sleeve or muff coupling. Okay, this is the diagram. Sleeve or muff coupling. Okay, here you can observe capital D. Here capital D is the outer diameter of the sleeve. Okay, and small d is the inner diameter of the sleeve, and also small d is the diameter of the solid shaft. Okay. Here, let's consider this sleeve or muff coupling as a hollow shaft. Okay. Sleeve or muff coupling is the simplest type of rigid coupling made of cast iron. Okay. Here, the cast iron is used for making the couplings. It consists of a hollow cylinder whose inner diameter is the same as the shaft diameter. Okay, the inner diameter of the coupling is equal to the diameter of the shaft. Okay, it is fitted over the ends of the two shafts by means of a gib head key, as shown in figure. Here, this is a key. Okay, this is a key. Key is used. Power is transmitted from one shaft to another shaft by means of a key and a sleeve. Okay. Here the power is transmitted from one shaft to another shaft. Okay, by means of a key and sleeve or muff. It is therefore necessary that all the elements must be strong enough to transmit the torque. The usual proportions of a cast iron sleeve coupling are as follows. Capital D is the outer diameter of the coupling. Capital D equal to 2 times the diameter of the solid shaft plus 13 mm. Okay, 2D plus 13 mm is the outer diameter of the sleeve, and length of the sleeve L equal to 3.5D. Okay, length of the sleeve equal to length of the key. Minimum length of the key equal to 3.5D. Okay, and length of the sleeve also equal to L equal to capital L equal to 3.5D. Where D is the small d is the diameter of the shaft. Okay, small d is the diameter of the shaft. In designing a sleeve or muff coupling, the following procedure may be adopted. This is the cross-sectional view of a coupling, butt or sleeve coupling. Okay, this is the front view. This is the side view. Okay. Now I am going to explain about design procedure of a sleeve or muff coupling. In first step, you have to design a suitable diameter of the solid shaft. Okay, first of all, you have to design a solid shaft. Okay, to transmit the required power from one shaft to another shaft, we need to design a solid shaft. So first of all, you have to use power transmitted by the shaft. Power P equal to torque into angular velocity. Okay, torque T equal to 60 into P by 2 pi n. Here omega is the angular velocity. Omega equal to 2 pi n by 60. Okay. Now for solid, here we are going to design a solid shaft. So you have to use a solid shaft formula. Torque transmitted by the solid shaft. Torque T equal to pi d cube by 16 to tau. Okay, this is the formula for solid shaft. Here small d is the diameter, outer diameter of the solid shaft, and tau is the shear stress. Tau is the shear stress induced in the shaft material. Okay. T is the torque transmitted by the shaft. Okay. From this formula, you can get the value of diameter of the suitable diameter of the shaft. Okay. From this equation, torque T equals 16 to P by 2 pi n, we can get the value of mean torque. After getting the mean torque, you have to substitute this value in this equation. Okay. After substituting the value of mean torque in this equation, you can get the value of outer diameter of the solid shaft. Okay. So this is the required diameter of the solid shaft. Okay. Now in the second step, you have to design a suitable key, suitable sunk key. Okay. Here we are using a gib head key. So we have to select proper dimensions. For that purpose, you have to select width and thickness and length. Width of the key equal to diameter by 4. Okay, and thickness of the key equal to T equal to D by 6, and length of the key in each shaft. The length of the key in each shaft. Here we are using a single key, but we have to design a key in each shaft. The minimum length of the key in each shaft equal to half of the length of the sleeve, that is L by 2. Okay, so small l equal length of the key, L equal to length of the sleeve 3.5D by 2. Okay, here capital L is the length of the sleeve equal to 3.5 times the diameter of the shaft. Okay, capital L equal to 3.5D total length of the sleeve. Okay, length of the key in each shaft. Okay, after that you have to check these dimensions. In case 1, you have to design a key on the basis of strength, shearing strength. Okay, torque T equal to L into length into width into shear stress into radius of the shaft. Okay. Here small d is the small d by 4 and d by 6. Okay, here also d small d. Okay, here small d is the diameter of the solid shaft. Okay, from this equation you can get the value of shear stress induced in the key material. Okay, in this equation you can get the value of compressive stress induced in the key material. Okay, this one also small d diameter of the shaft. Okay, so from this equation you can get the value of compressive stress or crushing stress induced in the key material. Okay, in third step you have to design a sleeve or muff coupling. Okay, so the material used for coupling or sleeve or muff coupling is cast iron. So the shear stress induced in the cast iron, you have to check the shear stress induced in the cast iron. Okay, so for that purpose you have to consider this sleeve or muff coupling as a hollow shaft. You have to treat this coupling, this muff or sleeve, as hollow shaft. Okay, let tau suffix c is the shear stress induced in the cast iron material. Okay, cast iron material or shear stress induced in the coupling. Here capital D is the outer diameter of the hollow sleeve. So capital D equal 2D plus 13 mm and inner diameter is a small d. Okay, so this is the formula for torque transmitted by the sleeve or hollow shaft. Okay, you have to treat this coupling as a hollow shaft. Okay, this is the formula for torque transmitted by the hollow shaft. Okay, torque T equal to pi by 16 into tau into d cube into 1 minus k power 4. Okay, pi d cube by 16 into tau into 1 minus k power 4. You can use this formula or this formula. Okay, now here k equal to inner diameter of the hollow shaft divided by outer diameter of the hollow shaft. Okay, here inner diameter is small d, outer diameter is capital D. So k equal to diameters ratio, inner diameter by outer diameter. Okay, now you have to substitute the value of torque, mean torque and outer diameter of the hollow shaft and diameters ratio k. We can get the value of shear stress tau c, shear stress induced in the cast iron material, that is shear stress induced in the coupling. Okay, so these are 3 steps used for design of sleeve or muff coupling. Okay, this muff coupling mainly consists of solid shaft, head key and hollow shaft, that is sleeve or muff. Okay, here there are 3 components. So you have to design 3 components. First one is solid shaft, second one is key, third one is sleeve or muff. Okay, now I am going to explain about a simple example problem on sleeve or muff coupling. Design and make a neat dimension sketch of a muff coupling which is used to connect 2 steel shafts transmitting 40 kilowatts at 350 rpm. The material for the shafts and key is a plain carbon steel, for which allowable shear and crushing stresses may be taken as 40 megapascal and 80 megapascal respectively. The material for the muff is cast iron, for which the allowable shear stress may be assumed as 8 megapascal. Okay, this is a given question. First of all, you have to identify the given values. Okay, here you have to design a sleeve or muff coupling. Okay, here the problem is design of sleeve or muff coupling. Here the power transmitted by the steel shaft is given, that is power P equal to 40 kilowatts. Okay, this is the power. Okay, 40 kilowatts is the power. 1 watt here. W is the units for power. Okay, so 1 kilo equal to 1000. So 40,000 watts is the power. Okay, 40,000 watts, or 1 watt equal to Newton meter per second or joule per second. Okay, and the speed of the shaft is given n equal to 350 rpm, and the material for the shafts and key is plain carbon steel. That means the material used for shaft and key is same. Okay, that means the shear stress induced in the shaft material and key material is same. Okay, so the allowable shear stress tau for shaft and key is 40 megapascal, and crushing stress for key as 80 megapascal. Okay, and the material for the muff is cast iron, for which the allowable shear stress may be assumed as 8 megapascal. That means shear stress induced in the cast iron material, that is coupling. The shear stress induced in the coupling is 8 megapascal. Okay, so these all are given values. So speed n equal to 350 rpm. Shear stress induced in the shaft material equal to 40 megapascal. 1 megapascal equal 1 Newton per mm square. Okay, and crushing stress tau c equal to, sorry, shear stress induced in the cast iron tau c equal to 8 megapascal. Now sigma c. Sigma c is the compressive stress. Compressive stress induced in the shaft and key material. Sigma c equal to 80 megapascal. Okay, 80 Newton per mm square. Okay, this is the diagram, sleeve or muff coupling. In first step, you have to design a solid shaft. Okay, so already we know that power transmitted by the solid shaft, power P equal to T into omega. Again, omega equal to 2 pi n by 60. Okay, so from this equation, the torque transmitted by solid shaft, torque T equal to 60 into P by 2 pi n. Okay, from this equation, you can get the value of torque, mean torque transmitted by the solid shaft. Okay, so 60 into here power P equal to 40 watts, 40 kilowatts. So 40 into 10 power 3, 40 kilowatts divided by 2 pi n. Here the speed also is given. Okay, after substituting the speed, you can get the value of torque. Torque T equal to 1100 Newton meter. Okay, here the power is in Newton meter per second. So the torque transmitted by the solid shaft also in Newton meter. Okay, after that you have to convert this meter into mm. Okay, 1 meter equal 1000 mm. So 1100 into 1000, 1100 into 1000 Newton mm. Okay, this is the torque, mean torque. After getting the mean torque, you have to use this formula, torque transmitted by the solid shaft. Torque T equal to pi dq by 16 into tau. Okay, now you have to substitute the value of torque T equal to 11 lakhs equal to pi d cube by 16 into tau. Already we know the value of tau s, shear stress induced in the shaft material, tau s equal to tau equal to 40 megapascal. Now you have to substitute the value of T and tau. You can get the value of diameter, outer diameter of the solid shaft, D equal to 52 mm, but the standard size is 55 mm. Okay, the standard size of a solid shaft is 55 mm. Okay, so this is the step number 1. This is step number 1. From this step, we got suitable size of the shaft. Okay. In second step, you have to design a key, sunk key. Already we know that from given question, the shear stress induced in the key material and shaft material is same. So tau s equal tau k equal 40 megapascal. Shear stress induced in the key material equal 40 megapascal. And the crushing stress or compressive stress induced in the key material is equal to 80 megapascal. Now here you can observe the value of compressive stress. Compressive stress sigma c is 2 times the a shear stress induced in the key material. Okay. So for that purpose, you have to use square key. Okay. When shear stress, when compressive stress is 2 times the shear stress, then you have to use a square key. Okay. So for square case, width and thickness both are equal. Okay. So the width of the key equal to thickness of the key equal to d by 4. D by 4 equal to 55 by 4 equal to 40 mm. Okay. And thickness also same for square key. D by 4 equal to 40 mm. And the length of the key L equal to length of the sleeve divided by 2. Length of the key in each shaft. Length of the key in each shaft equal to half of the length of the sleeve. Okay. Here the length of the sleeve is 3.5D. 3.5D is the length of the sleeve divided by 2 equal to 3.5 into diameter of the solid shaft 55 mm by 2 equal to 97 mm. This is the length of the key in each shaft. Okay. Now you have to check these dimensions. Design a key on the basis of shearing strength. Already we know that torque transmitted by the key, torque equal to L into W into tau into D by 2. L is the length of the key, W is the width of the key, tau is the shear stress induced in the key material, D by 2 is the radius of the solid shaft. Okay. Now you have to substitute the value of torque T, length, width, and radius. Okay. Now you can get the value of shear stress induced in the key material. Okay, shear stress induced in the key material. From this equation, the shear stress induced in the key material tau k equal to 29.4 mm, 29.4 Newton per mm square, 29.4 Newton per mm square. But from here you can observe from given data, shear stress induced in the key material is 40 mm. The induced stress is 29.4. Okay, this value is less than the given permissible value. Okay, so that means the design of key is safe. Okay, here the maximum stress is 40. The induced stress is 29.4. Okay, that means the key is safe on the basis of shearing strength. In similar way, design a key on the basis of crushing strength. This is the formula for key. Torque transmitted by key equal to length of the key into thickness of the key by 2 into compressive stress. Compressive stress induced in the key material into radius of the shaft. D by 2 is the radius of the shaft. Now you have to substitute the value of mean torque, length, thickness, and radius. Okay. From this equation, you can get the value of a sigma C. Sigma C is the compressive stress induced in the key material. Okay. Here you can observe the induced compressive stress in key material is 58.9 Newton per mm square, but the given stress is 80 megapascal. Okay, 80 megapascal. Here you can observe the induced stress is less than the given stress. That means the design of key is safe on the basis of crushing stress. Okay. In this equation, the key is safe on the basis of shearing strength. In this case, the key is safe on the basis of crushing strength. Okay. So totally the key is the design of key is safe because the induced shear and crushing stresses are less than the permissible stresses. Therefore, the design of key is safe. Okay. In third case, you have to design a sleeve or muff coupling. Let's consider this sleeve as a hollow shaft. Okay. Now, small d is the inner diameter of the sleeve. Capital D is the outer diameter of the sleeve. Already we know that shear stress induced in the coupling material is tau c equal to 8 megapascal. Okay. Here the material used for a sleeve is cast iron. Already we know that shear stress induced in the cast iron material is 8 megapascal, that is equal to 8 Newton per mm square. Okay. And here capital D is the outer diameter of the sleeve. That value equal to 2D plus 13 mm is the standard value for a sleeve or muff coupling. Okay. Already we know that D is the diameter, solid shaft diameter 55 mm plus 13 mm equal 123 mm. Okay. Small d is the inner diameter of the sleeve. Okay. Small d equal to 55. capital D equal to 123. This is the formula for torque transmitted by the hollow shaft. Okay, you have to consider sleeve as hollow pipe, hollow shaft. Okay, that's why I am considering torque for hollow shaft. Torque T equal to pi by 16 tau c into D power 4 minus D power 4 by D, or you can also use this formula, torque T equal to pi D cube by 16 into tau into 1 minus K power 4. Here K equal to inner diameter by outer diameter. Inner diameter equal to 20, sorry, inner diameter small d equal to 55 mm, outer diameter capital D equal to 123 mm. Okay, so this is the value of K. 55 is the inner diameter, 123 is the outer diameter, equal to 0.447. Now you have to substitute the value of capital D, small k, and torque T. After substituting these values, you can get the value of tau c, that is the shear stress induced in the coupling material. Tau c equal to 3.135. But in our question, already we know that shear stress induced in the coupling material is 8 megapascal. Okay, 3.135 is the induced shear stress. This induced shear stress is always less than the given permissible stress. Okay, so the design of our sleeve also safe. Okay, since the induced shear stress in the muff is less than the permissible shear stress of 8 megapascal, therefore the design of muff or sleeve is safe. Okay, so this is the design procedure of a sleeve or muff coupling. In next class, I will explain how to design a split muff coupling. Okay, in next class, I will explain how to design a split muff coupling. Okay, thank you.